Uh, okay. Alan, we can.
So today, Ignacio Ferreras will be giving us a talk. He's an honorary professor, right, at UCL and a researcher at IAC in Spain. So I think we can start.
All right. Okay, thanks so much. It's an absolute pleasure to give this talk, even though it's virtual. Let's hope that at some point I will get to visit you guys. It would be very nice to be there. So let me just share the screen here. Let's just see, so desktop. And you let me know, can you see my screen here?
Yes.
Yeah. Okay, and I'm going to start a presentation. So you can see the first slide, right?
Yes.
Okay, dokie. So, I'm going to talk about a bit of a mishmash of a mixture of things. All of them have the common thread of this title, Unravelling Galaxy Formation from Optical Spectra. And I also put as a subtitle, one of the most challenging inverse problems in general in astrophysics. As you can see from this figure, the bottom line is trying to see whether by using the spectra, especially focusing on the optical, NUV optical and infrared part of the spectrum, whether we can gain information regarding the processes of galaxy formation. But as I said, it's a bit of a mixture of different topics that I will put there. So by the way, here, this is my email address. So whatever I'm talking about, we can have a question time at the end of my talk, but feel free to drop me an email if you want to find out more about whatever I'm talking here. This preliminary slide is tremendously generic, so you can put it anywhere you're giving a talk on galaxies. Of course, we already know that galaxies are growing from fluctuations in the density field. We assume them to be Gaussian. They are caused by something we can talk about, inflation, as one of the main things that you go from very small scales to the galaxy scales. But the main idea from our point of view is that those fluctuations will grow via gravity in an expanding universe. They undergo a nonlinear phase. Go into a so-called process of virialization. So you're producing the so-called dark matter halos. And you have this bottom-up hierarchy in which you go from very small structures to larger structures. So this is, as I said, very generic. At this level, we separate overall the dark matter contribution versus the baryon distribution. And the baryon is the important one in a way for us, because this is the one that we can observe through telescopes. So the baryons, of course, will mean the gas that eventually cools down and forms stars. So in all this process, I would say the last sentence here is the one that drives our work in a way. We have a tremendously complex baryon physics that in a way produces an inverted hierarchy. Even though we have a bottom-up scenario, you go from small fluctuations to larger ones, the formation of galaxies can actually proceed in the opposite way. And it is much in the same way as sometimes you find very massive galaxies at relatively earlier times. So as you can see, it's a complicated way of connecting, on the one hand, the distribution of matter, so the dark matter overall dominating, and the actual observable universe, which is mainly in the form of gas and especially stars. So as I said, my talk concentrates on stellar populations. So you go from observables to physical variables. And the main idea is that if you take photons in the rest frame region from near ultraviolet, optical to near infrared, what you're actually seeing is the atmospheres of the stellar populations. Those stars will have a wide range of, if you want, mass, chemical composition, etc. And what you can do is you can use those stars as basically witnesses of the process of formation. So you can use the spectra of galaxies in this region that is coming from the stars as a DNA fingerprint. And of course, the idea is that we're understanding these spectra as being linear superpositions of different populations. So as you know, one of the fundamental concepts here we have is of stellar population, by which I mean a family of stars that have a common formation process. They have a common age, common chemical composition, etc. And what we do is we mix different types of populations according to the process of formation of the galaxy. So once more, another very generic slide. This is a figure from the review that you already know from Charlie Conroy, in the sense that most of the time, the standard approach to understand the spectra of galaxies is basically comparing the observables, so photometry, spectroscopy, with population synthesis models that are nothing more than just a combination, if you want, of these three key ingredients. You have a distribution of stellar masses, the so-called stellar initial mass function. Then you already know about stellar evolution. So you say, if I have a star of a given mass and chemical composition, it will evolve in this or that way. So then you can use a set of these types of isochrones. Basically, you simply evolve those stars, in which case you already know how many stars of a given mass will be there at a given time. And you combine those with a stellar library. So spectra that correspond to specific stars of a given, if you want, position on this isochrone. So you combine, put them all of them together, and you produce this type of composite, or well, spectra of populations that could be composite, simple, etc. But the bottom line is that you have a model value and you have an observable, and then you compare them. And this is a standard approach. The second part of my talk is going to be on something that is alternative to this. But what I'm going to do now, before I get into that one, is basically talk about two recent applications of this very generic method of comparing properties of the spectra of galaxies to understand specific issues of galaxy formation. As I said, the second part will be dealing with, in a way, an orthogonal approach to this problem, which is trying to understand the information content of galaxy spectra. So in this first one, this is actually the work done by my student, James Anthopo. He finished actually at the end of last year. Now he's a postdoc in Brera in Milan, working with the WEAVE collaboration. But most of his work, while he was a PhD student at UCL, was focusing on Green Valley. So as you know, Green Valley represents a very important transition region. We already know that when you're having a statistical distribution of galaxies, they come into flavors. You have star-forming galaxies and you have quiescent galaxies. The star-forming galaxies appear blue, and they populate the so-called blue cloud. And the quiescent galaxies have no ongoing star formation. They don't have any young stars, and they appear redder. And we basically, as you know, we put them on the so-called red sequence. In between those two families of galaxies, you have the so-called Green Valley, which represents a transition. In a way, you go from the process of forming stars in your galaxy to quenching, to stopping the process of star formation. And of course, Green Valley galaxies are very important because this region represents the most fundamental quenching processes that can appear in galaxies that we understand in the standard paradigm we have now could be caused by star formation, or it could be caused by AGN activity. In a way, you can have other things, but in principle, we separate them in these two general aspects. And this is very important. I'm going to super concentrate the work of James on his thesis on one specific aspect of his work. But the main idea is the reason why Green Valley galaxies are so important is that in order to model the process of baryon physics, of going from gas into stars, we need to introduce the so-called subgrid physics. As you know, we have hydrodynamical simulations that can trace in a very detailed way, if you want, the evolution of the gas. You also have a Poisson solver for the dark matter. So you already know how the dark matter evolves, how the gas evolves in this growth of density fluctuations. The problem is now you have to go from gas into stars. In order to do that, you really cannot simulate this thing from an ab initio point of view. And what you have to put is simple prescriptions, simple recipes. These are usually called subgrid physics because basically you don't have enough resolution within your grid to be able to trace those. So that's why in the end, even though we have a tremendously good way of processing numerically the evolution of the density fluctuations, both for the dark matter and for the gas, trying to understand the formation of stars is much more complex, and it ends up being a set of cartoonish type of ideas, such as the one we have here. This is already an old paper, but it is very representative. It's, if you want, established, well, it is one of those that presented the ideas that we have for the potential evolution from the blue cloud into red sequence. You can have mergers and quenching, etc. And these are the processes that we have to understand in our models. So in general, you need to be able to trace the baryon physics, but in the Green Valley, it is essential. In other words, what I usually say is if you use the Illustris or Eagle simulations, you can have very good estimates of very general trends like the stellar mass distribution or the age metallicity relation or the mass metallicity relation, etc. Those things in very general terms you can get. When you go to Green Valley, it is much more, if you want, detailed because you really need to be able to understand how the quenching processes operate. And this is where you're basically putting your analysis of the subgrid physics to the limit. So just to put it in a nutshell here, the novel approach of James was, rather than defining the red sequence, the Green Valley and the blue cloud from the point of view of colors or star formation rates, which are dependent on dust and any other systematics you need to correct for these things. Basically, we use the strength of the 4,000 angstrom. As you know, in stellar populations, this is one of the features that is very sensitive to age. There's also dependence on metallicity, but it's quite sensitive, especially for young ages. So the idea is that the 4,000 angstrom break, because it is a spectroscopic indicator, it is very weakly dependent on dust, which means basically we don't even need to apply a dust correction. And even if we do apply one, the systematics coming from that correction are going to be minimal. So this is the definition we have here. The idea is, the idea is for a given bin in velocity dispersion, we separate the blue cloud and the red sequence as Gaussian functions, and then we introduce the green valley as a third Gaussian distribution, and this is done in separate bins of velocity dispersion. So as I said, there's a lot of work behind it, and I encourage you to have a look at the papers that I will be presenting, showing in the slides. But for instance, one of the results that we get when we go into the green valley, by the way, this represents U is upper green valley, lower green valley. So basically we go to the upper region closer to the red sequence or the lower region closer to the blue cloud. And what we find is, in terms of the fractional contribution, as expected, you have a good number of star-forming galaxies, especially at the low mass end, at low velocity dispersion. You have quiescent galaxies mostly at the massive end. But the interesting bit is you have a very important contribution, fractional contribution of AGN. Again, this is nothing new, we already know, but this is already telling us that AGN are tremendously important in trying to understand the quenching processes that operate from blue cloud to red sequence. And not only that, you can see the AGN are there over a wide range of velocity dispersions, not only at the massive end. So this is an important part that perhaps we are familiar with the idea of AGN operating mostly at the massive end, but in principle, we have this over a wider range of masses. So, just to get to the point of what I want to say in the talk here, in this part, we wanted to say, okay, once we have an observational constraint of the green valley here, so we already know where these guys are, now we're going to go to the simulations. So we take two of the state-of-the-art simulations, Eagle and Illustris TNG. We use the 100 megaparsec box definition. And what we do is we use those models to produce a simulated spectra, much in the same way as what we find in the Sloan Digital Sky Survey, which is what we have here. These are observations, by the way, from Sloan. So we produce the same type of observations, and we try to compare them to put the subgrid physics to the test. And what we find is this. You can see in red, green, and blue would be that those are the observational constraints from Sloan. And then the data points and the contours represent the distribution of galaxies in the simulated version. So in Eagle and Illustris here. And you can see that overall, for instance, the blue cloud, well, don't make too much out of the fact that you have many more lower mass galaxies in the simulations than in the observations. That's, if you want, a bias that we have. In the simulations, we have many more low mass galaxies because of the, if you want, volume issue. In Sloan, because of the observational constraints, we have more of the brighter things. But the bottom line is that the blue cloud can be explained quite okay in terms of the 4,000 break. Basically, it constitutes an extension of this contour distribution. However, the red sequence appears significantly higher for the simulations. Basically, perhaps the age distribution, the stars there appear rather old for these types of things. So the bimodality is there. You can see that the distribution can be found. You can see here the observational one in Sloan and in Eagle. Pretty much you reproduce the bimodality in these two histograms, but you tend to have many more older, strong 4,000 break galaxies in the simulations. So that's one thing. We then what we did is automatically we went to the green valley, tried to explore the green valley, and we said, okay, if we go, the green valley can be broken, as I said, into upper green valley, lower green valley, and here if you want the mid green valley. So the three different positions, whether you're closer to the red sequence or the blue cloud. And here we do this both for Eagle and Illustris. We find the fraction of galaxies that are quenched as a function of the stellar mass of the galaxy. And what you find, the observational values are appearing as a shaded region, and the simulations appear as dots. You can see pretty much the observations and the simulations are more or less okay, but we tend to have a bit of an issue, especially at the massive end, and especially closer to the blue cloud in the lower green valley, which is namely when the quenching starts to operate. And this is especially relevant in TNG. You can see the effect is even stronger. We have many more quenched galaxies at the massive end in the Illustris. So you can see already that even though these simulations have been tested and matched and constrained with the simulations, when you go to the blue cloud, this is where you have much more of a variation that you can explore for the subgrid physics. So the way to try to explain this, as I said, I'm going super quickly into this, but the main idea is we already find that simulations have this excess of quenching. So one of the ways to understand this is find the cumulative distribution of stars as a function of their age, how many stars are being formed of a given age. And you can see this is found in these different panels from low mass to high mass. So at the low mass end, you can see that the comparison between TNG, so Illustris and Eagle. Now I'm only comparing simulations, so TNG and Eagle. You can see that they are not very different. I mean, there are some issues there, but you can see as you go to the mass event, this is where the biggest difference appears. The dashed lines correspond to Illustris TNG, the solid lines correspond to Eagle. You can see at the very massive end, let's have a look at the final plot here. In TNG, you're actually built up very quickly. So you have, let's say, if you go to Eagle, you have more of a gradual increase in the stellar mass of the systems, whereas when you go to TNG, you actually have a much more. Sorry, I said it the other way around. Sorry about that. So in Eagle, what you have is basically an increase of the stellar mass of massive galaxies, and then very quickly you stop star formation. Basically, you quench at earlier times. So you see the stars go up as you go from early times to now, and then suddenly the cumulative distribution gets horizontal, which means that you have very fast growth, and then you have quenching at earlier times. Whereas in TNG, in Illustris, you have more of a gradual increase. Okay, so this is a the most important point from this part of the talk I'm giving. The idea is that we are finding that in TNG you have a more gradual growth, which means that, of course, eventually, remember, we need to constrain this with the observational fraction of quenched galaxies at zero redshift. So automatically, what TNG have to do is apply very strong feedback. That's the only way of doing it, and this is our point. Basically, when we are comparing in the Green Valley, the observations from Sloan and the simulations, we find that the difference between a simulation such as Eagle and the Illustris TNG is that in the case of TNG, you have too high, too strong of a feedback. The way to try to explain this could be coming from the way these black holes are put into the centers of galaxies to produce AGN feedback. Remember, this is happening at the massive end. So our understanding of this is the following. Remember that in these models, what you do to produce a black hole in a galaxy, you just put it by hand. Once more, this is subgrid physics. There is no, if you want, hydrodynamics or detailed physics of the formation of the black hole and its growth. So the only thing you do is once the halo of dark matter surpasses a given threshold, by hand, you put a seed black hole in the center of the galaxy. And of course, then you let it grow. You let it grow through the simulation. So at that point, you can actually use the standard simulation to trace the evolution of it. What happens is the difference between Eagle and Illustris is that in Illustris, you have a substantial difference in the threshold mass of the payload to put the black hole and in the mass of the seed black hole. And in principle, the idea is that this threshold is higher in Illustris with respect to Eagle, which requires basically to put the black hole in the halo at a later time. And this is in a way our way of explaining why here AGN feedback perhaps is not strong enough at earlier times, but then it appears to be, it has to be very strong at later times to be able to meet the constraints. So that's our take on this part of the material that I'm presenting, that if you go to the Green Valley, it is a tremendously useful way of constraining the subgrid physics of the models. By using the 4,000 angstrom break, we get rid of a large number of systematics. Remember that if you use color, for instance, if you're not applying dust corrections, you may end up getting in the red sequence objects that are star forming but red because they are dusty. Of course, you apply corrections and you get rid of that problem, but then you introduce systematics. So by using the 4,000 angstrom break, you can overcome these types of problems. And we find basically this substantial difference in the feedback approach between Eagle and Illustris that in a way shows that Green Valley is a very important phase that could be exploited to constrain better and to understand better the processes leading to the formation of stars and galaxies. So that's my first talk. My first sub-talk, if you want. These are the references here, if you're interested. And as I said, you can send me an email if you have questions about this. The second mini talk that I wanted to include there was once more using stellar populations to understand galaxy formation, and in this case, the specific issue of environment. So the idea is that originally you have the process of galaxy formation as something local, something appearing in a relatively small scale. By that I mean the scale that extends over the halo of a single galaxy. So we could talk about 100, 200 kiloparsec, no more than that. However, we know that galaxies are living in a so-called cosmic web, as you can see in this image, which means automatically that the processes that relate to the presence of this environment, namely, if a galaxy is sitting in a higher density region or a lower density region, closer to a filament, closer to a cluster, those things are going to be affecting the process of galaxy formation. Of course, there are tons and tons of papers talking about this. I'm simply going to show some of the recent work that we have been doing. And one of those, this is a paper using the SAMI data. This is a survey of integral field unit observations. So you're taking spectra of individual parts of galaxies. And here we explored the gradients of the properties of stellar populations. But I'm not going to talk about gradients. That would take me a whole seminar for this. I just wanted to show you this figure, which is quite interesting in the sense of saying, look, what we can do is simplify the problem into the following sense. We can have two main drivers of the evolution of basically stars and galaxies. On the one hand, you have the local driver, which means all the processes that take place within the scale of a galaxy, or you can have the effect of environment, basically whether this galaxy is sitting in an over density region or a lower density region. When you're producing scaling relations such as this one, you can see here in this cartoon version, what I'm plotting here is the metallicity measured within a given aperture. Here it would be 1/4 of the effective radius. So this is metallicity as a function of, let's say, a local variable. Here, the local variable is a stellar velocity dispersion. We already know, as you go towards the right here, you go towards more massive galaxies, and we know those galaxies are more metal rich. So you have the data points over here. When you go towards lower mass galaxies, they appear on this side. So you have a well-defined, if you want, mass, if you want, metallicity relation, which in this case depends on the velocity dispersion. So out of this data, what I do is I produce a linear fit from which I get a slope. So the slope of the metallicity versus velocity dispersion relation, and the intercept would be the actual value of metallicity at a fixed reference point in velocity dispersion. In this case, I choose 200 kilometers a second, let's say a typical galaxy. So when I do this, I can produce the type of plots that you see here. This plot is supercharged. If you go to this paper, you will see, I mean, perhaps we put too much information in these plots, but the idea is, let's put it this way, if you only concentrate on the first set of 3 data points here, what I mean is I am producing a relationship between metallicity and velocity dispersion, as you see here, sigma. The slope is what you see here for 3 subsets. The complete set would be the gray data point. And then if I separate this according to environment, I basically have this point in red for cluster galaxies, this point in blue for field galaxies. I call this gamma because this is just coming from the general gamma survey, which is a part of Sloan, and this is mostly in field regions. So you can see already that there is, of course, a well-defined slope in the sense that galaxies are more metal-rich at high velocity dispersion, but this relationship tends to be steeper in cluster environments rather than in the field. So there's already an effect. You can see here an environment-related effect in the sense that when a galaxy with the same velocity dispersion lives in a higher density region, in principle, it tends to have a higher value of the metallicity. There are many more things in this plot, and as I said, I don't have time for this, but the idea is we also explored other local potential drivers. We have velocity dispersion, stellar mass, dynamical mass, the surface mass density, two-dimensional, the gravitational potential, or some sort of virial parameter, which is velocity dispersion over the size of the galaxy. The bottom line is that there is always a difference with respect to environment, but this is especially important and very correlated in the sense of velocity dispersion. Remember that velocity dispersion to some degree represents the steepness of the gravitational potential in a galaxy, and this is the one that dominates. So the idea here, the take-home message in a way is that you do have a very strong, tremendously strong local connection of star formation in galaxies. Basically, the properties happening over galaxy scales are most importantly the ones that dominate. But then you also have a subdominant effect, which is coming from environment. This is also something that has been done more generally. There's a very nice review done by Anna Pasquali already some time ago in 2015. And the bottom line is that when you're trying to explore the differences in the star formations of galaxies or the properties of galaxies, depending on where they are, let's say in the field or they are in clusters, what you find is that overall there are differences, but most importantly, it boils down to whether the galaxy is either a central, so it sits at the center of the overall gravitational potential of the overall dark matter halo of the cluster, or whether it is a satellite, which is a system that has fallen into this bigger structure. What we find in general, there are many papers. You can see here a very short list of them, and there are many more. I can send you a long list if you want. The bottom line is that what we find is central galaxies in principle can refresh their star formation from infalling satellites. So on average, they appear younger than other galaxies at the same velocity dispersion, at the same stellar mass. Satellite galaxies in principle tend to be quenched in principle quite quickly as they enter the group or the cluster. So this is, if you want, a general a relation that we always find. And in this context, we explored an interesting result that we published. I mean, there were two takes of this, one in 2017 and the other one in 2019. The idea is the following. Now, let's try to take this environment effect to the limit, and let's only consider basically close pairs, systems that eventually will end up merging. So you can see this can connect with how we understand the gradients of the stellar populations. So the idea is you have a primary galaxy, which is the massive one, and you have a satellite that is very close to it. Normally, we define this catchment area to be within 100 kiloparsec. So you can see within the region of the expected, if you want, a galaxy scale dark matter halo. And in redshift, we also impose a difference that corresponds to velocities of order a few hundred kilometers a second. So in principle, we expect those two galaxies to end up merging. When we do the analysis of the stellar populations, so you can see in this paper that we explore a wide range of properties there, we end up getting a very consistent result in the following way. So once more, we are considering a massive galaxy and the nearby satellite. And what we do is we separate the sample according to the mass ratio. This is this mu parameter. Mu is the ratio between the mass of the satellite and the mass of the primary. So we separate them in the sense that if you have a satellite that is very low in mass compared to the primary or high in mass compared with the primary, and what we find is that there is a very strong difference with respect to this mass ratio, in the sense that you have this mu3 sample. As you can see here from the distribution, mu3 corresponds to lower values of this parameter, which automatically means that you're basically, if you consider the same type of galaxy, the primary is more massive. So if you take all the galaxies within the same local property, you find that those that are closer to a more massive primary, in principle, will appear older. As you can see in this diagram, I'm plotting here age versus metallicity. So you see that in mu3, those guys appear to the right, they will appear older. The difference is not enormous. You can see this is a rather subtle effect, but it is consistent. This has been done by putting together a large number of galaxies and doing stacking or even doing individual analysis, as we present in this paper. And we find that the result is very consistent. The interpretation of this is could be quite interesting, because it's in a way the business that you may have heard about galactic conformity, in the sense that if a galaxy is in a given group, it already somehow knows that if it's in a group that is dominated by an old galaxy, it is going to be overall old. So in a way, there is some connection there. You can also connect this to the so-called fossil groups. Mu3 means that the satellite galaxy is much lower in mass than the primary. So this is closer to a fossil group. In a fossil group, what you have is a tremendously massive galaxy in the center and very low mass galaxies outside, very few and low mass galaxies. So that means the process of evolution has been going quite quickly. And then the way of interpreting this is through so-called assembly bias. This is once more very complicated. Maybe this will actually take a bit of time, but the bottom line is that in these types of studies, normally when we try to assign the properties of a galaxy to a given halo, we use a single parameter, which is the mass of the dark matter halo. So if you know that the dark matter halo is high, that means you live in a cluster. If the mass of the dark matter halo is lower, that means that galaxy lives in let's say in a group or even in a field, even if the dark matter halo is lower. So you see there is a single parameter associated to the dark matter. In assembly bias, it's as if we need to have a more complex description of this environment. So the mass of the dark matter halo is not enough. And then you need to consider that that dark matter halo may have assembled at an earlier time or at a later time. So in a way, the second parameter, so to speak, would be, for instance, the formation of that halo. We understand that these types of effects could be down to assembly bias. And once more, these are things that could be easily found in simulations. We haven't done much there, and perhaps as those of you who are working on simulations could be interested in exploring this type of project from, if you want, from a numerical approach, trying to see whether those differences are in principle found there. And on this traditional approach point, I'm just going to finish with a few slides on a projected phase space. This was actually mostly work done by a PhD student, Vitor Sampaio, working with Reinaldo de Carvalho. You know, I think many of you know Reinaldo and possibly Vitor as well. He has been doing very nice work on exploring the properties of the stellar populations and general properties of galaxies when they are in an environment by looking at the so-called projected phase space. By that I mean, rather than simply doing this very simplistic approach of environment as saying you live in a cluster, you live in a field, or you live in a low mass group, you try to introduce some dynamical information. Your galaxy sits at a given, if you want, projected distance with respect to the center of the group, and this is measured perhaps as a fraction of the virial radius, and you have a velocity that can be high or low compared to the overall velocity dispersion of the galaxies in the same structure. There is this very nice work done once more by Anna Pasquali, 2019, where they compared simulations. In simulations, they compared the locations of their galaxies in projected phase space. And a very interesting connection can be found between the location of your galaxies on this projected phase space, as you can see, and the color coding means the infall time, basically when that galaxy fell into the structure. This is, if you want, trying to go in more detail into the analysis of environment. Now you no longer consider cluster versus field. You say within the cluster, I'm, let's say, in a region where the galaxy is expected to have fallen at a very early time or at later times. For instance, in the core of the cluster, so this is region number 1, region number 2, you expect the infall time to be very early. So that's why you have 6 gigayears ago, the galaxies fell into the structure. Whereas if you're in this portion of the phase space diagram, so rather separate with respect to velocity, to position, and at relatively high velocity, those galaxies may have been fallen in the system very recently, like 1, 2 gigayears ago. Within this context, you can also separate these structures as whether they have a velocity distribution that is closer to a Gaussian or not. As you can imagine, I mean, even from the point of view of thermodynamics, if you have a Gaussian distribution, you're approaching more a stable situation. You have virialized somehow your system. Non-Gaussian systems tend to be dynamically younger. And there's a lot of work that has been done by Reinaldo de Carvalho. Vitor has, in his PhD work, has been looking into this, finding differences on these structures, whether they are actually parts of a Gaussian structure or a non-Gaussian structure. And interesting results were found. But I'm going to just show one more slide on this, concentrating on a specific type of galaxies called backsplash galaxies. So you can see this is a simulation, and this is a trajectory in the same projected phase space of a galaxy that sits here. So it's going to fall into the structure at location A. It falls into it, then it overshoots and goes away outside of the cluster, and then eventually, gradually, through dynamical friction, ends up falling and basically virializing into the structure. So there are galaxies that ironically appear outside of the cluster. However, they have been feeling the full impact of environment during this passage, and these are called backsplash galaxies. So these are galaxies are actually quite important because they also allow us to understand the details, once more, the subgrid physics associated to the effect of environment as a galaxy falls into a structure. And this is just the slide I wanted to show here, that we have done a recent work. This is submitted. I think we will be posting this in the archive very soon, within a month or so, where we have done once more an analysis in projected phase space, as you can see here, but going outside of the cluster. If you want, this is the radius, the radial projected distance. Here, this is within the virial radius. We go outside of the virial radius, and we separate them according to velocity, whether the galaxies have low or high velocities. The galaxies that go away but don't go so quickly, have low velocity, in principle, are supposed to have a large contribution from backsplash populations. Basically, these types of galaxies will end up populating as you can see here, this region of parameter space. So what we did is a comparative analysis of the stellar population details, properties of galaxies in this part and in this part of this diagram. Once more, data from the Sloan Digital Sky Survey. And we found something very interesting. The effect is actually a bit subtle. It's not very strong. But what we find, by that I mean, so have a look at this red and blue. Blue would be the population that should have an excess of galaxies coming from the backsplash population. And you can see red versus blue. The blue one appears to have slightly, these are stacked data, appears to have slightly higher 4,000 break, which in principle means older populations, perhaps more quenched populations. They also have weaker delta, Balmer absorption, H delta, once more representing older populations. The magnesium MGFE, it's about the same. You may be tempted to say slightly higher, but maybe perhaps not so much. So this is one effect that is quite important that we find, that there is this subtle effect. We measured in this paper, we presented this, there's a lot of detail, but the idea is we find an excess between 5 and 10%. It's not enormous, but it is actually substantial in the sense that we have, if you want, from 5 to 10% more galaxies here than here, that in principle could be explained by the backsplash population. So that's point number one. Point number two that I wanted to show, and once more here, this is a bivariate plot showing once more the red versus blue, so low velocity versus high velocity. And you can see on diagrams of line strengths, let's say 4,000 break versus Balmer absorption or MGFE prime, you see that there are differences. There are indeed differences there. The second effect that is much stronger by far is the following. Now we compare these two regions, which are the blue and the red, with this brown, which is a general population from the Sloan Digital Sky Survey, only homogenized to have exactly the same distribution in velocity dispersion, so that the local properties are the same. So in principle, we're comparing apples with apples. So in other words, the type of galaxies you see here, I then extract at random similar distributions of galaxies with the same mass as the ones you see here, but coming from the overall general distribution of Sloan. So those would be representing field galaxies. And you can see the enormous, highly non-subtle difference in the sense that the field sample happens to have much lower 4,000 break, much higher H delta. Once more, in this case, younger populations, they have younger ages, so perhaps more ongoing star formation. And not only that, even the MGFE prime shows actually lower values, so in principle, lower metallicities. This is the effect that we associated to pre-processing. By that, we mean these are not effects of the actual environment of the galaxy falling into the structure, but the fact that these galaxies, the ones that we find here in red and in blue, were formed in regions that overall have higher density in the general distribution of density fluctuations. So those galaxies will undergo a more, if you want, a faster, more efficient process of star formation, which leads to these differences in the sense that these guys undergo more formation at early times, so they appear older and they appear more rich in terms of metallicity. So these are the results that I wanted to present here regarding environment. So sorry, I think perhaps I'm going a bit too quickly over these things, but we'll have some time for questions. But I just wanted to finish with this third mini talk, which I think is very close to my heart in a way. This is something this is an important thing that I wanted to show you guys. This is work that I have been thinking about for a long time, but now we're presenting some papers out of it, which is the following. Those of you working on galaxy formation and evolution using stellar populations may wonder, when you use these sophisticated models of stellar, so you have the Vazdenkis models, the Bruchal-Charlot, the Conroy models, you see that you have enormously complex data. You have your spectra. You can produce spectra over a very wide range of, if you want, wavelengths at a high level of detail. So in a way, you have lots and lots of, if you want, data points to constrain. So let's put it this way. You have a spectrum of a galaxy. You may have 1,000 data points. So if you have 1,000 data points, you should be able to get super, if you want, constrained information of the populations. However, when you go to any paper on stellar populations, we end up talking about the overall age, the overall metallicity, perhaps Mg over Fe. Sometimes we can go into we may talk about a bit of quenching timescales, but very shyly. You see that we can only stay at a very rough level. We cannot really go into minute levels of detail in terms of the stellar population. So there is a bit of a conundrum here. Why do we fail in terms of trying to get detailed constraints on the stellar population content using a galaxy? So this is something that I was always thinking about. And as I put here, this was something I presented earlier in the talk. We have the standard approach, which is comparing basically our models with the spectra or the photometry, and then we just basically do a chi-squared likelihood analysis, whatever you want. But you do a statistical analysis comparing models and data. So is there an alternative way in which we perhaps are not tied to the, if you want, constraints given by the models themselves? You have systematics, you have etc. So you may try to see whether you can get the information directly from the observed data and only from the observed data. And there are methods such as blind source separation. They involve things like principal component analysis, independent component analysis. You can have also supervised and unsupervised machine learning, deep learning, shallow learning algorithms, those that basically just simply use the statistical properties of the data to try to extract information. But the bottom line is that when we're trying to get information from spectra, either using the standard approach or alternative approaches, all of these methods ultimately depend on the information encoded. If there's a lot of information, I can get it. If there is not information, I won't be able to encode it. And this is the big question. How could we possibly quantify in a fundamental way, independent of the models? How can I quantify the actual essential amount of information that we have in the data? And this led to this project that is based on the idea of entropy. So the idea is the following. Rather than thinking of the spectrum as a distribution of photons as a function of wavelength, which is the typical interpretation of a spectrum, how many photons do I have of a given, so how much energy do I have in a given part of the spectrum, I basically use the photon counter interpretation. I assume that I am observing the spectrum one photon at a time. So every time I get a photon, the photon has a probability of having a given wavelength or energy, if you want. So then I basically transform my problem from having a physics type of approach in terms of understanding the energy as a function of wavelength from my galaxy to understanding the probability distribution. This is now a probabilistic approach to the system. If we have a probability distribution, automatically we can measure the so-called entropy. Entropy, as you know, is a probabilistic description of surprise. How surprising is the fact that I'm getting a photon of a given wavelength? So for instance, a high entropy regime would be one where I don't really know. The photon can have any wavelength whatsoever. So I'm totally lost. A low level of entropy would be light coming out of a laser beam, in which case I know exactly the wavelength of the photon coming to my detector. So with that in mind, you can see I define the entropy just as a P log P integrated in wavelength. And rather than integrating it throughout the whole wavelength of the spectrum, I just define this within an interval. So what I can do is I can define a so-called entropy spectrum. In other words, I define the entropy, but not throughout the spectrum, within a window. And I choose this window to be of order 100 angstrom. This is where you usually get a decent amount of information. There's, once more, lots of motivation behind that. So at a given wavelength, I put a window of 100 angstrom, and then I basically I shift this interval, and I define my entropy spectrum. Or if you want the complement to that, which is the negentropy. Negentropy, in a way, means the amount of information. So whenever you have a high level of entropy, you don't have much information and you have very low negentropy. So it's one minus the other. The bottom line is the following. When I apply this to the models, once more, simple stellar population models, these are from Bruchel and Charlot. You can use Vazekis, you can use Conroy. The result will be the same. You can already see here, this animation corresponds to a range of ages. And you can see here, I'm sliding it. Basically, I'm considering every single wavelength. I'm not concentrating on those, if you want, brownish intervals. I'm basically producing the whole interval. But then you see that when I'm probing different ages for my distribution, most of the information, in the sense of entropy, happens to be located in these very specific regions, you can see. So it doesn't come as a surprise. After all, people have been working on these things. I mean, you have here Lick indices, you have the 4000 break, you have Balmer absorption, things that we already know and love. We have been applying this for ages on populations. But from an information theory point of view, it simply makes sense because this is where you have most of the information in the sense of entropy. So I think it's an interesting approach. Once more, I use the models just to illustrate that. If I use the real data, now these are Sloan data, Sloan spectra, so now there are no models to consider, and I simply separate them according to the nebular emission. So the BPT diagram, I separate them into quiescent, star-forming and AGN galaxies, and once more you see it's very similar. I mean, I just go to the next page. Here, these are whatever I have from the models, the animation that you have just seen, and these are the actual real spectra. And you see once more, doesn't come as a surprise, in terms of entropy, it appears in the same regions. Of course, on top of that, in the real spectra, you also have entropy in the regions where you have emission lines from the nebular phase. These are no longer stellar populations, so I don't go into that. I get rid of those guys. I just basically avoid those regions. But once more, you do have entropy, you do have information, of course, as expected in the star forming and in the AGN. Here in oxygen 3, especially in AGN, H alpha, you have both star forming and AGN producing this information. So I'm just going to briefly finish with the following. If we define, going back here, these 1, 2, 3, 4, 5, 6 regions where you have most of the entropy, and I apply a so-called principal component analysis, you do find these are the traditional line strength approach, but I want you to concentrate on this H bar, which is the neg entropy. You can see that principal component number 1, which is the one with the highest variance, happens to be mostly the 4000 break, the 4000 break signal, whereas the second order component happens to be H delta. I have not used any models whatsoever. Here I'm only using the entropy coming from the Sloan spectra. And you may recall many papers, the Galaxy papers, the Kaufman papers, where basically they concentrate on D4000 versus H delta. Well, you can see that from the point of view of entropy, those two variables make perfect sense because those are the ones where you have most of the information content. The third one is actually a bit more intriguing because you have, I mean, by the way, the size of these symbols are the amount, the weight given to a principal component number 1, number 2, or number 3. So here you see principal component number 1, most of the variance is dominated by D4000, 2 dominated by H delta, and 3, it's a combination of Balmer, both delta and gamma, as well as sodium. It also produces an important signal. And the other thing I wanted to show in this slide is the following. You can see this is basically the weights of the different eigenvalues in principal component analysis. When I use a traditional approach based on line strength, so what I do is simply going back to this region, I simply measure the line strength here in the traditional way. As we already know, you go to this region, you measure the equivalent width, and then you just put it in your principal component analysis solver. And what you get is, in that case, the variance is actually quite spread out over, let's say, well, I would say 4 principal components are needed to explain 95% of the variance. When you use entropy, in that case, rather than defining the line strength here, I just define the entropy here, the entropy here, the entropy there, etc. I do get a much more condensed representation where I have 95% of variance only in the first 2 components. And I'm just going to finish with a couple of slides that I think this one and then a thought-provoking one. This one is actually simply going back to the data. I already have my projections. I have my principal component number 1, which has most of the variance in neg entropy. So here I have 87.5% of the variance explained in this component. And I separate my galaxies with respect to their basically distribution. So I take the 5% of the sample with the lowest value of PC1 projections and the upper 5% of the distribution of PC1 projections. And then I plot some of the properties: velocity dispersion, stellar mass, redshift, and signal-to-noise ratio. And this is just to show that, remember, this is actually only coming from the information encoded in the spectra. What is the system getting? And remember, this is a machine learning method, especially an unsupervised one. We'll be looking for variations in a statistical way, much in the same way as entropy. It will be looking for entropy variations. So actually, it's interesting to see that when I separate them with respect to AGN, quiescent, and star-forming activity, you see that there is some difference, especially in star-forming galaxies, with respect to velocity dispersion. But most importantly, there is a very substantial difference. Well, you have here redshift and signal to noise. So we have to be tremendously careful as how we present the data to the system. Remember that now I'm not doing any model comparison. I'm only using the statistical distribution. So if I have a biased representation, for instance, if my signal is coming from signal to noise ratio, my differences, and then in principle, I could be biasing my results. This is very important for those of you working on machine learning approaches to the analysis of galaxy spectra. So this is very important. And I'm just going to finish, I think, yeah, it's already over time. So I'm just going to finish with 2 slides that are a bit of thought-provoking, which are the following. it all comes down to the information that you have in spectra. So let's actually make the simplest approach. Let's define the covariance. The covariance matrix now here is for the models. These are Bruchsal and Charlotte models. Once more, if you use other models, you will get similar results. Of these 6 regions, the 4000 break, H delta, H gamma, so Balmer, MGV, the iron region, and the sodium region. And I compute the covariance of these regions in my model data. You see the level of correlation is enormous in the following sense. Here you can see that a decorrelated data should have a matrix that should be closer to a unit matrix. Basically, all these off-diagonal terms should be close to 0. They are not, which means that every time you change one of those line strengths, the models will go in sync, which is very important because sometimes, for instance, you do spectral fitting. And it goes back to my original question today. You may have a spectrum with 1,000 data points. So if you do a chi-squared, you're going to do a chi-squared with 1,000 data points in your analysis. You go like, my goodness, I have superhuman constraining powers there because I have 1,000 units of information. But this is wrong. You can see in your models, your data points are so correlated that the effective degrees of freedom, and by that I not only mean the parameters, it's also the correlatedness, the covariance is actually so high that your effective degrees of freedom would be much lower than the ones you have. That's once more why we have a very tough time trying to constrain parameters other than age or metallicity. And I'm just, the final slide is, you have a look at this matrix, which is the one corresponding to models. I can produce exactly the same covariance for real data from the Sloan Digital Sky Survey. And this is what we get. These are the models once more, and these are coming from the Sloan data. And you can see that there is a high level of correlatedness that's substantially lower, which means that even though when we fit real data and models, you actually find that the chi-squared fits are very good, very close to 1. You feel so sure that your results are super correct. You see, as far as the covariance is concerned, there is an enormous difference, which is basically telling you that the real universe is much more complicated than the synthetic universe. Somehow it makes sense, mainly because remember, these are models coming from Bruchsal, Charlotte, Vazdeckis, etc. All of them are superpositions of stellar libraries. The Milles stellar library has about 1,000 stellar spectra, no more than that. So no matter how many models you make, you can actually produce 1 billion models, but you're doing this with superpositions of 1,000 stars, which means basically the level of correlatedness you have in principle could be too high. And I'm just going to finish with that part. I mean, my final part of the talk, I hope it is tremendously thought-provoking, especially for those of you that are driven into machine learning methods, because those methods tend to basically try to get information from the variations in the spectra, but those variations are tremendously tricky, as you can see there. This paper is actually in referring process, but we will be getting it accepted relatively soon. But you can actually see a preliminary version in the archive. So I think I will finish there. Thank you.
Thank you very much, Ignacio, for the very nice talk. So now if people have questions, please. First, people here in the audience. No, so maybe people on Zoom. Okay, so no, okay.
I do have a question.
Yep.
Okay.
Actually, more than one. So this last method you presented, the entropy method, so seems to be very nice and very powerful in the way of quickly fitting a large amount of data, let's say so, because it seems to be much faster than, for instance, a full spectral fitting. So my very first question is, what is the best separation you can find in age using this method? So, or in other words, how precise is the age you find, for instance, separating two populations, not a mean age, but the different age steps?
Yeah, a good point. Well, so I would say, on the one hand, this method is nice in the sense that it produces an orthogonal way of thinking about things, and it reduces the dimensionality. So as you're saying, you can fit things much faster. It is not very unlike, in that respect, it is not very unlike to methods such as VESPA that you may know about, or the older one was called MOPED, in which what you do is basically you separate according to the distribution of information. There they use factor analysis or a Fisher matrix approach, but you try to get the essence, the variance of the information in terms of few parameters. So rather than having to fit 1,000, you only fit, I don't know, 5 or 10 or 20. So you get results very quickly, okay? And that's good. The problem is I still find that those results actually have to be taken with a grain of salt, much in the same way as this method as well. The problem is the second, your second part of your question. It's a nice method. You can do this quickly, fine. How well can you discriminate? And the problem is you cannot discriminate so well because going back to this, for instance, this one here. Let's see if I actually let me just produce this one, the animation. So if I go, there, so this is where this done. So this one. So when you see that when you're actually changing the ages, when they become, well, when they are very young, here you start having very strong variations, which is the typical things you expect when you're basically your turn of mass goes around A-type stars. So you have strong thing. But when you go to very older ages, you can see that it also gets stable, which means automatically that the spectra don't change that much. I mean, this is something we already know. When you go for it changes very quickly, but once it gets very old, it stops there. Yeah. So my answer to your question is that even though this method produces an alternative way about something more essential, unfortunately, it will have similar types of problems in terms of trying to discriminate small variations, let's say in age or chemical composition. I mean, I was tempted to call this type of material that I'm presenting something like the Gödel theorem version of stellar populations, in a sense that there's so much we can get from the data that we cannot get anything more, and it is a bit annoying. It's like a barrier that we have. I mean, let's put it this way. So the question would be, can we come up with a method that allows us to discriminate ages in this level of detail that we need? And unfortunately, from this point of view, which is very fundamental, it seems like it is tremendously hard. Of course, the best approach, if you ask me, would be rather than going for full spectral fitting or a convolutional neural network method with all the data points, targeted line strengths in principle will give you more information. So, for instance, when you try to constrain things like the stellar initial mass function, you try to basically go to 3 or 4 indices at as high signal to noise ratio as possible. Those depend in a minute way, 1% maybe, but they depend in a way that you can control. And perhaps my gut feeling, which in a way converges with Alex Vazdeki's point of view, is that perhaps spectral fitting is in a way much more informative. When you produce these general approaches, you're basically lost in terms of this information that you have. And you can see from the entropy, the level of entropy we have is actually very close to, I mean, this is, I had to multiply this by 1,000. If I had to say in terms of bits, I would say with very few bits, you can encode all of the Sloan Digital Sky Survey with a precision of 1 part in 10,000.
So it's very, very quick.
Yeah.
So actually the other two questions, they were answered in your answer to the first question, which merely means, so if it is better go back to the indices way or to continue the full spectral fitting. So it's
indeed. I mean, I would imagine that there are more things that could be there. I mean, smart combinations of different parts of the spectrum could be done, but you have to, in a way, bend over backwards. It's very difficult, really, to try to extract things in a way that you already, for instance, I was mentioning the IMF. You already know that in general, we find these trends in the variations of the IMF, but when you try to do this in detail, you basically hit your head against the wall of the systematics coming from the analysis of the line strengths. You have a dependence on age, on metallicity, on other abundance ratios that automatically are going to mimic changes that you expect when you change the initial mass function. So, but I would say if I had to bet on one, I would say line strength analysis of targeted, well understood lines would be the way to go. Yeah.
Thank you.
Any more questions? Here, no. I have one question, Ignacio. I don't see the camera is over, but I'm here. Yeah, I'm curious about what you presented about on the Green Valley galaxies. Yeah, generally we assume that the green valley are galaxies that are transitioning from the red sequence to the blue cloud, or the blue cloud for the red sequence. But what do you think about the possibility that are some galaxies that lead there? They are really the green valley galaxies that are. What are 2 cents about this?
Yeah, that's a tremendously good point. You could say, in principle, we all the time we use this argument of the fact that you can see that there are very few galaxies there. This is like the Hertzsprung gap in stellar evolution. We have very few objects there, which means there has to be a transition going from one place to the other. As you're saying, either most of them going from blue cloud to red sequence, or as you're saying, also red sequence to blue cloud via some rejuvenation event. Your question is very interesting. Could you have a fraction of those? Those are going to be very small nevertheless, but could you have galaxies that in principle have more of a stable phase of evolution, that they could be somehow sitting in these regions? Well, it's a good point, and in a way it connects with the fact that these variations are also connected with the changes that we have in stellar populations. You know that when you change your stellar populations, you very quickly go from, let's say, a very low value of the 4000 break to a very strong value, and this happens also quite quickly. And this is the sweet spot. Is at around 1-2 gigayears. That's why every single paper that talks about green valley, in every single paper, you will see that the timescales are of order 1 to 2 gigayears. There is no surprise there, because it is mainly because of this. Somehow you can see that if you consider the green valley as a stable thing, you have to keep the age of the population there within that relatively small value. So that would be unlikely. That's the way I would put it. That because you have such a strong transition in the populations, in principle, you expect these things to take place relatively quickly. In other words, if you try to produce a population there, you have to somehow, as these populations get old, you have to get a highly synchronized star formation rate to keep the average age at the same value. Or you have to produce a replenishing, so six-source type of argument that in principle would boil down to galaxies going from blue cloud to red sequence. It's a very good point. It's a thought-provoking idea.
More questions? Okay, so let's thank Ignacio again.
Thank you.
And okay, I'm just going to stop the